I am Daniel Humeyer. I am the Business Development Manager here at Spectrum Center. And I have with me Technical Support Specialist Ricardo Rodriguez. And today we're going to demonstrate a relatively new feature of the Spectrum software product. It is called the Map Maker. And it has the capability to convert map data, produce map data from what we would call raw materials. Today we'll focus on the conversion of raw LiDAR data. We'll talk a little bit how we acquire the raw LiDAR data and how we proceed to convert it so it's compatible with the Spectrum software. We will give a little bit of background into LiDAR data for anyone that's not familiar with it. And we will have a brief product demonstration on the conversion process with the MapMaker tool. And we'll have a very brief Q&A at the end. So we anticipate this webinar to last about an hour. And it will be recorded. So we will share the webinar with anyone that registered for this session. I think there was a number of people that registered but maybe weren't able to make the live presentation. And it'll also be on our YouTube channel as with all our other webinars. So brief overview in the agenda. We'll have a brief introduction, product line overview. Then we'll go over LiDAR technology in general, talk about the LiDAR conversion process, and then proceed with the product demonstration. The product demonstration will be handled by Mr. Rodriguez. So brief introduction, who we are, what we do. We are Spectrum Management Specialists. Our business is in the focus of reselling commercial off-the-shelf software, in particular our Spectrum product for spectrum management and spectrum engineering. We offer our product with two licensing options, either software as a service or SaaS subscriptions or perpetual licenses. We also provide enterprise solutions and related asset building services, leveraging modified off-the-shelf implementations of adapted versions of Spectrum. We do provide professional services as we hold a GSA multiple awards schedule with the U.S. federal government, and we do provide subject matter expert consultation services, measurement drive testing and coverage reporting, GIS data conversion, and custom software development. The product that we're going to highlight today is called Spectrum. It is a spectrum management web application, and it's composed of the following principal modules: e-licensing, technical analysis, and remote monitoring. The MapMaker feature is part of the technical analysis module. The platform includes an online portal, I should say maybe a web browser-based portal that allows end users to access a centralized repository of spectrum management data, either through a private network or over an internet portal. This aspect, we're not going to touch on too much today. We're going to mostly focus on the technical analysis module, and a lot of our focus will be how we use the tool offline, not necessarily as an online portal, but in future product demonstrations will probably focus a little more on the online portal. And actually, I think for our next one, we'll be focusing on maritime ship station licensing and how we can assist with applicants that wish to process a ship station license. The Spectrum product includes diverse implementation options. Here on the left side of the screen here, you have what we call a local implementation. So this could be in a private network or intranet, a client server install. This would be closed off from the public. You could even have a completely disconnected installation, such as on a disconnected laptop or workstation. So you don't need the internet for Spectrum to work. You have also what we call the cloud option. So this is kind of intuitive. We leverage our commercial cloud to provide the product to our customers, and just anyone with an HTML5 compliant web browser. So you could be using a smartphone, a Mac, a PC, a tablet. The platform is cross-platform compatible and touchscreen friendly, so the interface will adapt to the device that you're using. And yeah, all you need is an HTML5 compliant web browser, which are pretty much all the major web browsers. Don't need to install anything. Just get a login credentials and you're ready to go. Then we have a third option, which is becoming increasingly popular. It's known as hybrid cloud. And hybrid cloud basically is a mix of the previous two options, where a portion of the system may be hosted in a private network, but a portion of the system may be used through a web service call to our system's API, and that part of the install would still reside on our commercial cloud. So in this example, you have this local server that has Spectrum installed on it, but not all of it. Maybe, for example, it has a heavy computation it needs to perform, but there's not enough computing services or computing resources in the local install, the local server. So it'll leverage our commercial cloud resources, make a web service call to our API, and our API will produce the output and return the result to the local environment. So that's what we call a hybrid cloud. All of these implementation options can be synchronized with each other as we distribute product updates, security patches through a common portal that we offer to all our customers. So if whatever install that you have, whether it's a hybrid cloud or a local, if you're missing a particular update, you can always just go to the online portal and get that update, get that security patch. So you make sure to have the latest version of the product. And obviously the cloud install is always being updated contiguously. So we'll talk a little bit about LiDAR data. We'll go over technology definition, scanning techniques, the conversion process that we undertake on our side to convert the data, and some sample profiles using high resolution terrain and clutter data, and compared with not using high resolution, or what we call medium resolution terrain and clutter data. So first, I want to provide a definition of the term LiDAR. It stands for light detection and ranging. LiDAR is a method for determining ranges at a variable distance by targeting an object with a laser and measuring the time for the reflected light to return to the receiver. This is the Wikipedia definition. There are terrestrial, maritime, airborne, and mobile applications for LiDAR. Airborne mapping techniques are utilized to accurately measure the height of the terrain and surface objects on the ground. A LiDAR camera and processing unit are mounted on an aircraft, which can be a drone, helicopter, or plane, and through the use of a scanning laser, the distance between the aircraft and the ground is measured. We're going to focus primarily on the airborne mapping technique because we'll be looking at how LiDAR data can be used in telecommunications modeling, network modeling capacity. So we'll be looking at primarily drones, how drones are used to do LiDAR. Basically, the other options using planes or helicopters bring different benefits, but obviously cost is a big one. There's a big cost saving with using a drone as opposed to commissioning a flight or a helicopter. But you can fly at higher altitudes with the plane, for example, so you could cover potentially more ground, but perhaps with not the same level of granularity. And here you have a little example of a LiDAR scan. Kind of looks like a heat thermal image of the Capitol building. One thing we'll focus a lot on is sources of data. And in the US, there's copious amounts of LiDAR scanning done all over the country. And DC is well covered. And actually our demonstration today will highlight how we convert some LiDAR data from DC to the format used in Spectrum-E. Technique, if we focus on airborne LiDAR scanning, the technique that is undertaken, which we'll talk about a little bit, produces a number of products that aid in the creation of a digital surface model or a DSM. So here you have a diagram on the right that describes the aircraft. In this case, it's a drone. It's got some different components installed on it. You have a GPS, which is a global positioning system, and that helps provide the coordinates of the aircraft that contain what's known as a LiDAR scanner, which you have here at the bottom, little camera at the bottom here, and then an inertial navigation system, also known as an INS, also referred to as an IMU, or that describes the output of the system, inertial measurement units, and that describes the orientation of the LiDAR scanner in space. And so this is referenced with some ground control points that are also obtained prior to performing the scan. And when the scan is performed, basically multiple laser pulses from the laser scanner hit various parts of the canopy. What's known as the first return DSM information is created from the first or only LiDAR pulse returned to the sensor and contains all the ground and surface objects. So we can see that in this diagram. I want to go ahead and change the pointer here to make it a little more obvious. You can see that here you've got this laser pulse going down into the ground, and at certain points it'll hit a house or a building or a tree, and it'll return quicker to the LiDAR equipment. So it's obviously, as a result, more likely to return elevations from the top or near top of trees or edges of buildings, and that can be used in what's known as canopy height modeling or clutter height modeling, and the production of building outlines. And you also have, in addition to that, what's known as an intensity surface model, and this measures the amount of laser light from each laser pulse reflecting from an object. And this information can help describe like different categorizations of light intensity and differentiate things such as vegetation from roads, from buildings, from water. You also have what's known as a last return, and the last return would be the slowest returns, and that's generally going to hit the bald earth terrain. So here you have some examples of these last returns hitting the ground, and they're coming back obviously slower than the first return. So the conversion process overview is as follows. We first acquire LiDAR source data. There's many online sources in the US and a lot of developed nations in Europe and other places as well, where this information can be obtained for free because it's ultimately funded through taxpayer money. So there's a lot in certain countries for a public resource for online LiDAR data. When there's not that availability, private companies do specialize in reselling LiDAR data, and that can be contracted for a fee, obviously. LiDAR scans are becoming more and more popular, so these would be custom scans, and there's a lot of companies developing all over the world that specialize in this. This LiDAR technology is becoming a lot more flexible and economical, and really drone technology is kind of changing the game. There's a lot of economically priced drones that can be acquired all over the world, and you can buy this equipment almost anywhere pretty easily from Amazon, from a lot of sources around the world, and you can make your own LiDAR drone and do some scans. Obviously, that may require clearance with the local jurisdiction, but that is an increasing possibility. So then that information has to be acquired. The coordinates, obviously, of the aircraft and LiDAR scanner are also important in getting the source data, the source raw materials. So then the second step would be converting the raw LiDAR data to production formats to be used with MapMaker. So those production formats inside a MapMaker allow us to edit the data, to clean up the data before we turn it into the final production, the final format that's going to be used in Spectrum-E. Then we will produce what are known as the digital surface model and digital terrain model layers. Then we edit and clean up the data, removing spikes, stamping roads, etc. Then we produce the quad tile. So the quad tile is the organization, the cartographic organization that Spectrum-E uses. We'll describe a little bit how that works. And then we upload to Spectrum-E either online or offline. And we'll cover that in the product demonstration as well. So Spectrum-E quad tiles, what are those? They're an open, web-friendly cartographic format. This is not necessarily an invention of Spectrum Center. This is kind of how a lot of mapping tools such as Google Earth, Google Maps, Bing Maps, etc., manage digital cartographic data. You can see an example here where you have basically all the mapping data in the world broken up into different levels of tiles at different resolutions. So that makes it very easy to zoom in and out and view multiple layers of information at different resolutions depending on your zoom level without having to load, so to speak, mapping data constantly into a computing memory buffer or anything like that. So it is open format. All this data is in a PNG or JPEG format. So that allows this quad tile structure to be highly economical and scalable. It's very web friendly. Because they're open formats, they're PNG and JPEGs, then there's no need to load, it's web friendly and it's very compatible with GIS tools or even comic graphic image editing tools such as Microsoft Paint. And because you can cover the entire planet this way, you don't need to load separate projects with different cartographic area limitations and fixed resolutions and cartographic projections. So that makes it very friendly when you need to, let's say, model a national network or something like that, which becomes a need more and more these days. And as mentioned before, it is network friendly. The point of the quad tiles is to store all the GIS data in one central location so that everyone can share it. So that could be a private server or a commercial server. And that also helps avoid errors in reproducing results, as everyone can use the same source data in their analysis, and they don't produce potential differentiations because what kind of GIS data they used or how their particular computer loads that GIS data, which can be based on its computing resources, its memory, available RAM, this sort of stuff. So as mentioned before, the first step is to find a source of raw LiDAR data. The good news in the US is that there's many, many sources. One of the most popular sources is known as the 3DEP LiDAR Explorer platform. It's a system from the USGS. That's the United States Geological Survey. So it's free online. Here's a snapshot of the UI LiDAR Explorer, the interface here. There's a link as well if anyone wants to test it out. And as you can see, there's like green tiles over this map of the US highlight where LiDAR data has been acquired and stored. 3DEP stands for 3D Elevation Program. And it's basically how the USGS is storing GIS data, not specifically LiDAR, all kinds of data. But they do have a specific repository for LiDAR point cloud data. And here you can see this legend describes at different resolutions what's available in different parts of the country. And as you can see, most of the country is pretty well covered. The vintages can range from the early 2000s to as recent as this year. We also have the National Oceanographic and Atmospheric Administration, or NOAA, that has an online data source known as the Digital Coast Digital Axosphere, and here's a link as well. And it primarily obviously focuses on the coastlines, and this is oftentimes a very good source of getting very recent data, especially during hurricane seasons or these types of events, weather events that may require emergency LiDAR scans to cover a particular area, see how it's been affected by a flood or something like that, or a hurricane or a tornado. And so if you want to get a lot of very recent vintage data, all from along the coast. NOAA Digital Coast Digital Access Viewer is a very good source. They also do cover a fair amount of Alaska, I think the more populated areas of Alaska, and I think all of Puerto Rico and a little bit of Hawaii. If those sources don't work, there's several state and local county municipalities or city municipalities that do LiDAR scanning and do provide this for free online. Sometimes it's not, they don't have a very user-friendly user interface to get this information. You may have to call them and contact them, but they generally don't charge, or their fees are very low. They'll only charge for shipping, maybe maybe they give you the data on a USB thumb drive or something like that, and they'll charge for the shipping or something like that. So yeah, sometimes they don't have a very good online portal to get this, but that has to be researched. So generally that's the process we go in the US to getting LiDAR data. If there's a need for it and we can't find a public source, we can always contract a commercial customer, but obviously that comes at additional price and obviously takes a little more time. UK, we have a number of sources. I'm sorry, we have one specific source that we use is the UK Department for Environment, Food and Rural Affairs, known as the DEFRA, has a national LiDAR program, and here is their website, the DEFRA Survey Data Download site, and it's got LiDAR data with vintages as old as like 2002, but over the last 19 years, you see they've pretty much covered just about all of the UK pretty well. They do update this regularly. I think every year there's updated LiDAR scans that are put on here, and so that's a good source. Outside of these areas, you just have to contact your local GIS institute or cartographic military organization, see what they offer. I think in Latin America and in other parts of the world, a lot of this is more covered by commercial entities such as telco operators or gas and petroleum companies, or just other private industries. So it's maybe a little trickier to get it for free, so to speak. You may still have to pay a fee to buy it from a reseller, but it's becoming increasingly prevalent. And over time, generally the cost of this information, this data kind of goes down, especially if you wait a few years, the vintage gets a little older, it's not worth as much, so you can get a little cheaper and it can still be pretty good quality data. It may not be the most recent stuff, but not bad. So I think in time around the world globally, LiDAR data will just become more prevalent and easier to obtain in general. So what does the raw LiDAR data look like? Here's a screenshot of an ASCII file that represents the raw LiDAR information. And so you can see it's got a number of values. It can be a little confusing because it's got all kinds of information such as the GPS coordinates of the LiDAR scanner, the IMU orientation, scanning angles, pulse returns, coordinates of the ground data points, intensity values of scanned objects, etc. So that information is typically retrieved. The most common formats are LAS and LAZ. But here I wanted to show a text format just to make it a little, presentable, because the binary format's a little trickier to look at. But that information obviously needs to be processed and converted to a format usable for what we want to do in our particular industry, which is propagation modeling. So that would be involving various tool sets. The one we're going to highlight today is the Spectrum E tool and the MapMaker feature, and we're going to show how we produce a raster image file out of this raw LiDAR data. Here's kind of the end product to a degree, one of the end products. It's a digital surface model, raster image of the post-processed raw LiDAR data, and you can see it's describing flatter terrain, above ground obstructive data, such as vegetation or man-made obstructions, etc. And the point cloud data in particular takes advantage of the intensity values taken from the LiDAR scanner that is obtained in the LAS or LAZ files. And so those discrete LiDAR returns can be classified into ground, low, medium, and high vegetation classes. It can be differentiated from, let's say, road surfaces or bodies of water. So you can get a really good capture of the canopy layer. You can get things like tree heights. You can get things like heights of telephone poles. All kinds. You can even capture the elevator units or elevator cages or air conditioning units on top of buildings. All kinds of little pieces of information that could be very useful in modeling certain types of wireless technologies. It's like a 3D representation here of what the point cloud data kind of looks like. So why it's called point cloud. It's a lot of points inside this 3D matrix. Looks kind of like a cloud, and it's representing the vegetation intensities that are captured in this raster file. It's highlighted in this red square. So how do we produce the DTM and DSM data? So what we first do, obviously, is we take the first return information, and that's all the flat earth and above ground obstructive data, such as vegetation, man-made obstructions, and so forth. In this diagram, these blue points represent the pulse return points from the LiDAR scan. And they're obviously capturing just everything that is at ground level or above ground level. What we then do is we filter the DSM data to differentiate the non-ground points, and that's done in this diagram in this red. They've been colored red, so all the red dots are classified as non-ground points, and all the ground points are differentiated in this blue color. Then we will remove the non-ground points. As you can see, that's been removed. And using interpolation techniques, we can produce the DTM or digital terrain model after we've removed that. So we'll interpolate between the blue points and we'll create this kind of a bumpy, slightly jagged, bald earth terrain representation of just the ground. So here's kind of in spectrum what it looks like. You have here the LiDAR based digital surface model, and it's got everything captured: vegetation, ground. You've got the Washington Monument here. You've got buildings, and so forth. And this is obviously created from the generally from the first return data, and then what we'll do is differentiate that from the last return data, and we apply those filters to then create, and the interpolation feature to create this what we call DTM digital terrain model. So you can see it's got just terrain information as much as possible differentiated from the above ground canopy layer or clutter data. And some areas where there's no data, such as bodies of water, also have to be corrected. That's part of the correction and editing process to make sure there's no gaps in the model. And then sometimes in the process of interpolation or in the process of removing or differentiating the above ground points from the ground points, you can create artifacts such as spikes, things like this, and that all has to be cleaned up as well. We'll show how that's done a little bit with the MapMaker tool. So here we have a path profile in the SpectrumE tool where we're not using any LiDAR clutter. So we have no particular clutter heights, just bald earth terrain and generic clutter categorizations. So you can see the path profile here is represented by this blue line. That's the line of sight. And then the blue ellipse at the below, underneath that, this represents the two frontal zones. And the red curve is the free space loss. The x-axis is the distance between the 2 points in the profile in kilometers, and the y-axis is the elevation value. The gray area represents here the terrain, and the orange curve here represents the path loss along the profile. And you can see kind of dips at certain points when the receive point would be, let's say, dipping to a certain point where an obstruction could be created between the transmit and receive point. In the profile, this is generally transmit to the left and receive to the right. So this is one type of profile where you don't have anything above the ground. Because we separate the DTM and the DSM information in SpectrumE, we can, for the same profile, elect to introduce the clutter data, the height information. So here's the same profile, but I've pulled in the DSM clutter information. Obviously changes the profile a good deal, brings in a lot of obstructive data, will change the path loss calculation, and changes things around a little bit in how the path profile is calculated. So that's generally what we call high resolution data. That's generally considered 1 to 5 meter resolution. And LiDAR data is one of the sources to allowing us to produce those high resolution clutter data sets. Okay, and here's just some examples of the type of product we can produce using LiDAR data. We can capture tree heights, bushes, different vegetation, building heights, like houses and so forth. Here's an airport with a coverage overlay generated using the SpectrumE tool. And we do also support the conversion of DTED level 5 data, AutoCAD data. We talked a little bit about how we produce quad tiles, and we'll demonstrate that. And SpectrumE can also load vector files, shape, and KML, KMZ files as well. Okay, so that's it for the PowerPoint overview. We will now switch over to Ricardo, and he will handle the product demonstration.
Good morning. Are you guys able to see and hear, see my screen and hear me? Can I have a thumbs up if you guys can hear me?
Yep, looks like everyone can hear you okay, Ricardo.
Perfect. So I will go ahead and begin my presentation. So here's SpectrumE with the map maker currently open. Before we do dive into the map maker, I just want to go over similar to what Daniel mentioned. So I went ahead and obtained my LiDAR and actually used the LiDAR Explorer website from USGS. And in here, you can select an area of interest. So I put a little square just around the Washington monument. And then just asked to obtain LiDAR. And here it shows me an area of interest. And basically, it's showing me that for that for that Washington monument, it actually has 2 tiles, and we can see here on the right side it's showing 2. And if I hover with my cursor, you can see that it's highlighting in yellow the area of interest where those 2 tiles are covering. And by using this website as a reference for the tiles, and of course I downloaded them. I'm not going to download them right now, but by using this website as a reference, I pinpointed the upper left corner and the lower right corner I used Google Earth by using this imagery. So I'm going to pull Google Earth up. So here I have my upper left corner and lower right corner. And we don't have to be exactly precise where those 2 points are. All I want to have is a general idea where they are located. Also in Google Earth, the other thing I did, so I plotted them manually just to match what I saw on that LiDAR Explorer website. And then from here, what I did was just in tools and options, I activated the UTM, Universal Transverse Mercator latitude and longitude. And with that, I went ahead and verified the coordinates that are in each of the place marks. So I use this as a reference to where my LiDAR is located. And basically, this is usually my first step is obtain the LiDAR and then just verify the location of them. And then I use this inside of SpectrumE to build my project, or basically my data set. So this is the usually the first step I do so that I have, since I just downloaded the data, it's still fresh on my mind. I still have all that information up. So I obtain that and I just plot in my points. So then back in SpectrumE, the next thing I do inside SpectrumE, like I mentioned, everything is still fresh. My coordinates where I downloaded the data set. So then my next step is in the map maker tool, which is in the data store, is to create a blank matrix. And from here, when I press on it, I will insert my coordinates. So my upper left latitude and longitude, and my lower right corner, again, latitude and longitude. And then the grid code, I put WGS 84, so that's where the 4 comes from. And then UTM for Universal Transverse Marketer. And because this is north, north of the equator line, it's going to be UTN. And then 18, and 18, I obtained that information from Google Earth. So 18 is the zone code. And you can see on the bottom right corner, it tells me 18 inside of Google Earth among the coordinates. So I use that for my grid code. The next thing I do, of course, I can give it any name I want. So I could just say blank matrix dot SC2. So our production format, the extension. I could give it any name I want. Usually I put the name of the area, but just to showcase it. Um, and of course, this is a LiDAR. It is a 1 meter resolution. So for the step, I am leaving it with 1 meter. So 1 meter resolution. And then at the bottom, WMAS level. Basically, that's the zoom level similar to, it is actually what we see in the map of SpectrumE, the different zoom levels. And for this one, resolution of 1 meter, the zoom level would be 15. So for a resolution of 10, the zoom level would be 12. Resolution 30, the zoom level would be 10. In this case, would be 15. Before I do press to create, the next thing I will do is extend to level. So this extension to the level, basically what it's going to do is take into consideration my area of interest, and then it's going to extend my area of interest to match our quad system format. So we need to have the area that fits our quads. So I will press here one time, so extend to level, and you'll see the upper left corner, lower right corner will be modified. And of course, the number of points in X and Y axis, those will also be increased. And just to show a case, I'm just going to take a screenshot here, and we'll put it to the side, press extend to level, and you can see that the values have been modified. So basically, they've increased accordingly. Now I'm gonna play a little animation just to showcase. So this is the my area of interest. Inside of this blue square is gonna be my area of interest, and inside of it we already have the LiDAR already processed. But when I did the extend to level, what I did was just apply the calculation to figure out the quad area that's going to be needed. So the quad area will look similar to this black grid. So you can see that the area has been increased. So my area of interest is now bigger, and the reason why it's bigger is just so that when we cut it into tiles in the final product, we have that area of interest, so we don't end up with a tile that has some information and some information missing, which would cause you a big issue when you're trying to do a calculation, any calculation of your coverage of your signal, leaving the, let's say, leaving here the Washington area that I have data and going to where I have no data, and that could cause a basically here we're not far off from the ocean level, but imagine if you were, let's say in Colorado, where you could have high elevations, it would be a big drop of elevation and your signal would not look good. So you want to just make sure that you increase the area, and then we're going to fill in any area that is missing as well. I'm going to close here this little animation just to elaborate just imagery so you can see what I'm talking about. And in the end, Daniel did mention, it's going to cut it into quads, into tiles. And basically here's a representation. It's not an exact representation of what it's going to do with this one, but it is a representation of what it's going to do. Instead of being one file, it's going to be cut into 20 files, 20 tiles. I'm going to close that and close here. Well, minimize the snip. And I'm going to close here. I already have, basically I've created the files for each step of the way, so I don't have to run it. But essentially you would press to create. So I'm going to close here. And what I did create, I already have it here. So like I mentioned, I have one file for each step of the way. So here's the blank matrix that I already have created, and it's ready to go. So I can just select it, highlight it. So one click, it gets highlighted. Second click, it deselects it. When it's highlighted or selected, just open the SC2. And from here, we can view the file. So this is a blank matrix, so it's empty. So there's no information on it besides our area of interest and our coordinates. And we can always modify, we can always add. So you can see here at the right side, I have a polygon tool, fill, transform, and so forth. We'll talk about it momentarily about those functions. So for right now, I'm going to go back in the data store, going back to my file list, and we're going to now start working with our LiDAR dataset. Again, I just like to do that. The create blank matrix is my first step, just because I still have fresh in my mind where my area of interest is. So now just to verify the LiDAR dataset, so I have here two examples. I have one in Maryland and I have one in Washington, D.C. Actually, I have two in Washington, D.C. So the ones I downloaded from the LiDAR Explorer from USGS. And one is LAS, so that's the LiDAR dataset. The other one is LAZ. LAZ is just a zip format of LAS. So I'm going to select one of the LAZ. And then on the left side, gonna execute the LAZ info. So in the info, so the source file, the one I currently have selected, and I can modify it, insert the name of the next one and execute it. But for right now, I'm not gonna modify the name. And the report, we have two options. We have just the header only, or we have the header and the points. So I'm gonna do the header only for this one and gonna execute, press OK. And it's going to verify the dataset and return the information for this LiDAR file. So in this one, we can verify the different information here. The main thing I want to verify right away is going to be our units. So in this case, we can see here the vertical unit geo key is linear meter. So that's perfect. I don't have to do any modification to this file. It's already in meters. So SpectrumE is going to work in meters, not in feet, feet or other units. So we need to make sure that we have our units in feet. And we also have the coordinates in UTM format, so that's also perfect. So I don't need to do anything with this file. I can right away work with it. I don't have to do any conversion. So I'm going to close here and I'm going to showcase it, and that's why I have the one here in Maryland. So LAS info, and going to show you with header and the points on this one. And for this one, it actually is not in the correct unit, so that's why I want to showcase it. So here you can see the information, and in this one is actually in feet, in US feet. So this one would need to have a conversion done to it. Then the next thing I just want to showcase it is going to be the point information. So here's just giving us that extra information with the points. And Daniel mentioned it, but inside the LiDAR, you can have classifications of what each point is. So here you can see that some are unclassified, or actually a majority of them are not classified. We have some that are classified as ground. We have some that are noise, and a few other ones. You can also have them classified as water, for example. And I believe this one in DC actually has that classification, where it just shows you multiple points are being classified as a water area. So here we go. So we have here 1,600,000 points that are classified as water, some as rail, and multiple other ones. So you can see that the LiDAR even has its own classification inside the file. So I'm going to close here. So these files are basically ready to go, that I can automatically just use them. But let's say my Maryland one, it's not ready to be used. I would have to do some modifications to it. So basically the modifications I would have to do on that one is doing the conversion. So I would select the LAS file and do the Geo Conversion for that file. And from here, it's just going to ask us what is the source EPSG. So I would have to just research what the EPSG code is. I would insert that code, insert my units either in feet or meters. I want it in meters, so I would just leave it with meters. And then the destination UTM zone, I would have to specify that one. And again, Google Earth will tell us the UTM zone. So this one is 18S. It's still north, but it's S for the area. And they just to classify that EPSG is a registry code, and you can find it online in multiple different sources. You can find this information. For example, in a GIS tool, you could search for that coordinate that you want, and you could insert it. For example, for the UTM 18, here would be the code. WGS 84 UTM zone 18 would be 32,618. You can even do a online search for it. So here's what EPSG stands for, European Petroleum Survey Group. And if you search just the area of interest, you can see it will return you the code as well. I'm not going to convert this one. I'm just going to press close. I want to keep that with feet just for demo purposes, so I don't want to modify that Maryland LiDAR file. So back to our DC file. So this too would be my DC tiles around the Washington Monument. So I would select, I could select both of them and run the LAZ export to MTX. So this one would just start exporting my LiDAR dataset into my blank matrix. Now, the first thing I would recommend is, before you execute it, is to go to your blank matrix. So I have it right here, and duplicate that file. The reason I recommend that is, one thing to keep in mind is there is no undo. So when you do a modification, it's going to stay there on that file until you remove it, clean it, and so forth. So I personally would tell you to just create copies of it. And not just that, as Daniel mentioned, we're going to have the DSM and the DTM layers. So I will create copies of it, which I already have them made. So I have here my first return and my last return already made. So I just make copies of that blank matrix to meet my requirement. So then selecting the files, I would do the export to MTX. And from here, what it's going to have is going to be the source files. So it will have the list of files, and then the destination. So I would have to pick the file that I want to insert my LiDAR information. So I would pick my SC2 file. So I would say, let's, for example, I would pick the first return DSM, and then the type. There's a first return and the bare earth. So for the broadcasting purposes, we don't need the second, third, fourth return. We just are more interested in the first return and the last return being the bare earth. So that's the only two that we're going to focus on. And because my destination matrix, I did name it as the DSM, which is my first return, I would leave it the first return, and then I would press to run, and it will basically grab the LiDAR data and convert it to meet my SC2 file. So I'm going to close here, and I will showcase the DSM file. So like I said, I already have the files ready in each step of the way. So select it, open the SC2 file, and here we can see the first return. So here's what the first return is looking like, and it filled in my my matrix. And of course, you can see that LiDAR is great, but it's not a perfect. So there's multiple artifacts that should be cleaned up, and we can always just clean it up. We can always modify the SC2 file. So we could just use the polygon tool, for example, and just press on the polygon, and then you can draw your polygon around however you want. I'm not going to be precise right now. When you're done, just right click and it will close the polygon, and then the flag, the value that you want to insert inside that polygon. So just to showcase it, I'm going to put a 500 just so that we can see the polygon being drawn. I'm going to press OK, and there's the polygon. Obviously, it is going to be a zero elevation in real life, but just to showcase it, you can see that the polygon gets drawn. We can use the fill option. So with fill, just press the insert the crosshairs where you want it. So I'm going to insert it inside this polygon, use the fill capability, and from here, just insert the new value that you want to insert inside that area. Just press OK, and it's going to fill that polygon. So as you can see, now the polygon got modified to the elevation of 0. The transform capability is going to be somewhat of a query. That's, in my opinion, the best way to describe this capability. So you just request to modify one value, or all but one value, or all the values lower than, or all the values greater than, and then you insert that value that you want. So let's say all values less than or greater than 500, modify it to, and then insert the value that you want to modify that value into. Negative 9,999, that means no data. And right now I don't want to do any modification, so I'm going to press cancel, but you can see that you can do those modifications. Going to press close here. And you can do multiple other modifications from here as well. So I'm not going to do any modification. I'm going to leave it as is for right now. Going back to the data store. Going to verify the DTM as well. So here's the last return DTM, open SC2, and basically the same thing. I can verify the file, I can validate and do modifications to it as well. Back in the data store. So I have that done. The next thing, and this doesn't need to be the next step, it could be even before what we just did, but I did obtain the 20-meter data set. And this 20-meter data set is actually for to cover that area that is currently missing. As I showed in the quads, there's an area that is missing on that on my file because I didn't obtain LiDAR to cover every single area. So I did create here the 20-meter data set, and it's actually a much bigger area than what I needed. And it's better to be safe than sorry. So I cut a bigger area than what I was needing. From here, I did create, again, I grabbed the blank matrix, created a copy of it, and then I inserted my 20-meter into that 1-meter data set. So opening that 1-meter data set, I now have interpolated that 20 meter data set into this 1 meter file, this 1 meter matrix. And basically, I'm going to use this file to fill in the areas that I don't have data. Back in the data store. So now I have all those files ready to go. I could start basically stamping them to create my final product. Before I do create my final product, I would like to just notify with the cleaning. There's multiple cleaning that you can do, whether it's when you open it and creating those polygons to clean up area, or add. You could even add buildings to that area. Any building that is newer than your LiDAR, you can add it, or buildings that got removed, you can remove them from your data set. But there is a cleanup spike capability, and this cleanup spike, if you run it, it's going to clear any spikes that are in your data set that are basically out of nothing. One real good example for this function, why you would need to use it, and there is areas in this data set that I did not clean up just to showcase it, and we'll see it later on in the webinar. But it's basically sometimes you will have a bird that flies right below the your LiDAR device, and then you have a point in the map that is higher than your trees, higher than your buildings, in the middle of nowhere. A few months ago, I saw a user that in their LiDAR, they actually had a flock of birds that were flying below their plane. So they actually was a couple of birds that were flying above the a river, and basically you could use the cleanup spikes to remove those points, which would be birds, and for intensive purposes for broadcasting, you don't want to be considering birds. So you can use these cleanup spikes to remove those spikes that are in the middle of nowhere. And if you have areas that have no information, no data, those negative 9,999 points, you can interpolate and fill in those points as well. So the next thing I'm going to do is going to be to start stamping my points. And to stamp the points, what you will have to do is grab, for example, that 20 meter data set that's been interpolated into the 1 meter to have all of your area of interest filled in. So I have no area that is no data. And then from here, I will grab the my first return, for example, and I will do insert. And from here, I will have to pick the destination. So destination would be, let's say that 1 meter data set where I have the 20 meter that has been interpolated into the 1 meter. And then I would insert all my points except for no data points. So there's multiple options that you can use. And for this one, I would want to insert all but no data. All the values would basically just copy your file into another file. Even the no data points would be copied, and I don't want to do that in this case. And add values to the destination. It will basically just grab, let's say, 1 pixel in my DC underscore 1 meter. Let's say I have a 10 meter elevation, and then my DSM has 30 meter or even 11 meter. That add values to the destination will add to it. So then you will become basically the 10 plus, let's say the 11, and you will now become 21. And I don't want to do that either. So I would, for this case, I would want to all but no data. And would press to run, and I would start stamping the information. So then it would look similar to this case. So I'm going to open it, and I have my Disro terrain that I filled in with the 20 meter, and now I have the high resolution right in the middle of anything that I have. And the next thing that I also can do would be to just grab the vectors. So here I have building footprints, I have Washington DC roads, I have Washington DC boundary, and basically all these shape files I obtained from Open Data DC. So their website, the government website, you can search for data sets. So here's roads 2013, which the last update has been September 14 of 2021. So we can just download the dataset, in this case, directly from the government. And we can grab and I'll showcase it. So here's the blank matrix. So just to double check that it's blank, so there's no information on it. I can grab the roads. Here's the shapefile. I can rasterize it. And from it, it's going to ask what is the destination that I want to insert it into. Let's say I'm going to say the blank matrix. The grid, I'm going to leave it with WGS 84 decimal. That is actually the corner code for my my shapefile. Then the flag, the height that I want to be added to it. But however, for this one, let's ignore it until we get to the, in a moment, I'll explain more detail. The line width is the thickness of the lines representing my shapefile. So this width is going to be the pixel number. So in my blank matrix is a 1 meter resolution. So if I insert a 1, the thickness of the lines that represent my shapefile is going to be 1 meter. If I put 3, so then it's just a multiplier, 3 times the resolution, which is 1. So now my lines will be 3 meter thickness. The elevation, it's a drop-down menu where you can specify what field actually has your elevation. So in this shapefile, it is just the roads. There is no elevation on it. If there was, I could pick one of the fields that represent the elevation. So for this one, I'm going to tell it use the flag. And by saying use the flag, it's going to use that flag field. So from here, I can tell it what the height would be for my lines. And of course, this is the road, so I wouldn't want to add a height, but because I'm just doing a demo, I will put a 10-meter height just so that we can see something being added to my blank matrix. Can tell it to run, and basically that will add the roads, or it will stamp the roads into my blank matrix. So I'm gonna open, and here you can see the roads being added to it. And again, this is just DC, so anything that goes past DC, it's not going to have those roads. But I can stamp this into my final product as well to add more resolution to the areas that currently don't have any resolution. And just to showcase, I have a little animation of the stamping process. So here's the low resolution, and then I stamp the 1 meter resolution. So then I have here the DSM being stamped into my low resolution or my medium resolution data set. And basically the low resolution data set is just filling in areas that I have no data. And then on top of it, I can stamp the roads. So here's the stamping of the roads, and you can see the difference that it makes. And of course, you wouldn't want to add heights for the roads. This is just for a demo purposes. You could use, for example, the building footprints that I have downloaded from DC, for example. And just a zoomed in method. Here's Washington, DC around the Washington Memorial. Stamping the high resolution, and you can see the Washington Memorial there and the different buildings, and then stamping the roads onto it. So you can see the difference that it makes, the precision that you can add with all those modifications. So back in the data store. So then I have here my final product. So open the file. And there's my final product. I can still do modifications to it, so it's not, I call it final, but it can still have some modifications. I could add more of where it cuts off my LiDAR. I could continue with it, either add more tiles to it from LiDAR, or even manually modify and add the buildings to it. And then clean up spikes and so forth. So going back to the data store, now that I have both my DSM, and now let's just open the DTM just so that we can also see the DTM. And here's the what the DTM is looking like. And just zoom into the area where we actually have between the high resolution, the data set, and on the left side where I no longer have the LiDAR data set. So you can see the difference on both of them. Now that I have my two final products, I can select either one of them. I could still do the cleanup spikes if needed. In this case, I'm not, just showcase what happens if you don't have your spikes cleaned up. And then press create tiles with one of the files selected. And in here, first, just going to define the level. I'm going to leave it level 15. Prefix, I'm going to add the prefix. In this case, I will do a PQ, as in private quads. Underscore, the name of the file or the name of the dataset that I want. And for the name, please don't use any underscore. So I could say DC 1M, or I could even put a dash here, just separate, just to say what my my area of interest and my resolution. And then the next thing is my suffix. So the suffix becomes very important. And for level 15, you will have both DTM and DSM. So just double check what you have selected. So in this case is a DSM dataset. So my suffix should be DSM. So modify and place a DSM. If I actually had the DTM selected, I would insert here DTM. So the suffix will be modified for level 15 to have the DTM and the DSM, but the prefix, you should add the same one. So leave the same prefix for both the DSM and the DTM, just modify the suffix, just so that the software knows that both of them are from the same dataset. The prefix is going to be important to be the same or equal on both cases, just the suffix will be different. And then you would tell it to run, and I already did, so I'm not going to run it right now. The next thing, we're just going to go to the map. So now we did create the tiles, and in the map, I'm actually zoomed out, but that's fine. I'll go in network, select the Western Monument map selected object. So it just takes me directly to where it is. And here's my two in green, my two areas of interest. So I have the bigger one where I cut the 20-meter resolution, and the smaller in green is actually a representation of my LiDAR area. And I already have the digital terrain turned on. So I'm seeing the digital terrain, and I'm going to zoom in, and I have just this point here just to represent where the monument is. And I'm going to zoom in to level 15. So we can see that in level 15, everything is blank. There's no information, and that's fine. I have my quads, but I did not activate them. So that's why I don't see them. Going back in the network, going to go here. On the left side, I'm going to use the update terrain tiles. From this, I'm going to select my data set, which is the DC LiDAR. And right now I only have DC LiDAR. Going to activate it, press run. And from here, it's going to be active, and I can see it now in the map. And you will only see the 1 meter resolution when you're zoomed into level 15. And just to showcase it, where we have the crosshairs in the map, and in this case I put it on top of a building. Zoom level 15, so we can see here the level 15. We will start seeing the 1 meter resolution, and we can see two height fields. The first one being our elevation, so it's 9 meters above sea level. And then we have the building height, which is 21.2 meters above the digital terrain. And if I put the crosshairs on a place where I don't have a building, let's say the street, then the height is going to be 5 meter elevation above sea level, and 0 meters, there's no item or obstruction artifact above the digital terrain. So no tree, no building, and so forth. Back in the network, so I already have here a DC mobile, so I'm going to go back in the network, and I'm going to run a coverage calculation with that DC mobile. So I'm going to select it. On the left side, I'm going to run 1812, and I can run any propagation model. Just keep in mind, the different propagation models can take into consideration high resolution. Some are not compatible with high resolution. And in here, I'm going to leave the default parameters: 1 meter antenna height, 1 kilometer for my distance to calculate. I'm going to modify the clutter resolution to be high resolution. And then I'm actually going to ignore the clutter losses for right now, and profile sampling of 1,000 points inside of 1 kilometer. That's perfect. So I'm going to leave it and just going to run it, apply only to the selected objects. So only that one mobile is going to be calculated. And here's the process. So it finished calculating. Going to select the mobile once again, and now I'm going to tell it to generate my coverage plot, and I'm going to use a fill strength coverage plot, so a DVU talkout or the downlink. So going to have my fill strength. Going to leave the default name for the prediction process, just selected objects, and now I can see that in the map itself. So you can see my coverage from the map. And I'm going to modify the display options, remove the digital terrain from being displayed. For the background, I'm going to modify it to be, let's say, photo, and update. And now with the photo background, what I'm going to do, I'm just going to press on 3D so we can view that in 3D mode. I'm going to rotate a little bit so we can see the 3D, the buildings in 3D. And my coverage inserted, and you can see basically the down the street where I have better coverage, and where I have buildings blocking my coverage stops short. Now here's one good example, and it might be hard to view, but he actually caught here a little artifact that looks to be in the middle of the street. So to me, that's going to be a bird that got caught in the LiDAR as the first return. So that's why you would want to run data cleanup spikes to remove artifacts like that one. And it is, and you can see that it's much higher than the buildings. So that is going to be a bird that got caught when the LiDAR sensor was going off. I'm going to deactivate the prediction really quick, and going back in the map and just showcase it from the Washington Monument 3D view. And here we can view again just the 3D view, Washington Monument and area surrounding. There's that one spike that I mentioned, which again, it's going to be a bird on that one in the middle of the street, higher than trees and higher than buildings. And we can increase the terrain factor so we can view a little bit more drastic. And with that, I'm going to pass back to Daniel.
Okay, thank you, Ricardo. So we'll open up for questions and answers. I'm going to pause the recording. I think we're okay for the recording.